Welcome to this lecture on power and energy. We will start with electrical quantities, fundamental and derived units, and scientific notation. Then we will bring these concepts to life through human activities. Sports, the human body, your mobile phone battery, and your monthly TANGEDCO electricity bill. By the end of this lecture, power and energy will no longer be abstract. You will feel them in every step you take. Here is the most important analogy in this lecture. In mechanics, you already know that velocity is the rate of change of displacement. In exactly the same way, power is the rate of change of energy. If you run a long distance, your displacement is large. If you run very fast, your velocity is high. In electricity, if you use a lot of energy over a long time, you have high energy consumption. If you use it very quickly, you have high power. The fundamental relationship is P equals dW by dt. Hold that thought. It will explain everything in this lecture, from your heartbeat to a rocket launch. The International System of Units, SI, divides units into two classes. Fundamental units such as meter, kilogram, and second are defined independently. Derived units are built from combinations of these. For electricity, the ampere is the one fundamental unit. From it, we derive the coulomb for charge, the volt for potential difference, the watt for power, the joule for energy, and the ohm for resistance. Notice the beautiful logic. Every quantity you will use in electrical engineering traces back to just one base unit: current. Remember this chain. Ampere leads to everything else. In engineering, we deal with quantities ranging from picoamperes in sensor circuits to gigawatts in power grids. Writing out all those zeros is impractical and error-prone. Scientific notation lets us write any number as a value between 1 and 10 multiplied by a power of 10. Engineering notation goes a step further, restricting powers to multiples of 3, so each exponent maps directly to a named prefix. For example, 4700 ohms is written as 4.7 kilo ohms. 0.000033 farads becomes 33 microfarads. Memorize the prefixes from pico to tera. You will use them every single day as an engineer. Let us make energy real. 1 unit on your TANGEDCO bill is 1 kilowatt hour. That equals 3.6 million joules. A typical Tamil Nadu home with an air conditioner, a refrigerator, 3 fans and LED lights consumes around 575 units per month. The air conditioner alone, running 8 hours a day, accounts for 360 of those units. Under the current TANGEDCO domestic tariff, the first 100 units are free. From 101 to 200 units, you pay 2 rupees 25 paise per unit. From 201 to 500, 3 rupees 50 paise. Above 500, 4 rupees 60 paise per unit. For a 575 unit household, the estimated bill works out to approximately 1,620 rupees per month. Every time you leave the AC on unnecessarily, you're converting electrical energy into heat and paying for it. Every time you look at your phone's battery, you see milliampere hours. 5,000 milliampere hours means the battery can deliver a current of 5 amperes or 5,000 milliamperes for 1 hour continuously. Converting to energy, multiply charge by voltage. A typical lithium cell is 3.7 volts. So 5,000 milliampere hours gives 18.5 watt hours or 66,600 joules. To feel how much that is, it is enough energy to lift a 100 kilogram person up 68 meters, yet your phone drains it in a day. That tells you how energy-hungry modern electronics are. A higher milliampere hour rating means more charge stored, not more power. Power depends on the voltage and current drawn at any instant. The human body is a sophisticated energy conversion machine. Food provides chemical energy in the form of carbohydrates, fats, and proteins. When you digest a cup of rice, it releases about 206 kilocalories or 861 kilojoules. Your cells convert this glucose into a molecule called adenosine triphosphate, ATP. Think of ATP as your body's rechargeable battery. Every time a muscle fiber contracts, it hydrolyzes one ATP molecule, releasing approximately 30 kilojoules per mole. Your heart alone hydrolyzes about 40 kilograms of ATP every day. A typical adult requires 2,000 to 2,500 kilocalories per day. Divide by 24 hours and convert. and that gives an average metabolic rate of about 100 watts, roughly the same as a household light bulb running continuously. You are a 100-watt machine. Here is a fact that should make you proud of your brain. It consumes only 20 watts, yet it outperforms any artificial neural network in creativity, intuition, and generalization. At one-third the power of a laptop, the heart does roughly 1 joule of mechanical work per beat. Multiplied by 70 beats per minute and 60 minutes per hour, that is 4,200 joules of mechanical output per hour, about 1.2 watts of useful power. And here is a surprise. Chess grandmasters during intense tournament play have been measured burning over 6,000 kilocalories per day, comparable to elite marathon runners. The mental stress of deep calculation drives metabolic rate to 3 times its resting value. Mental work is real work. Chess is not a passive game. Let us use a simple staircase to separate energy from power in your mind forever. A person of 70 kilogram mass climbing one floor, about 4 meters, must do 70 times 10 times, actually 9.8 times, to convert kilogram force kgf to newtons times 4 equals 2,800 joules of work against gravity, regardless of speed. Joules is a Newton meter. If this takes 30 seconds, the power is just 93 watts, comfortable. If you run up in 8 seconds, the power is 350 watts, exhausting. Your muscles hurt because the power demand is 4 times higher, not because you did more work. The total energy expenditure is identical. This is the fundamental difference between energy and power, illustrated without a single circuit diagram. Walking looks effortless, but it is a constant battle against gravity. With every step, your entire body mass rises about 4 to 5 centimeters and then falls back. This up-down oscillation is the primary energy cost of walking. A 70-kilogram person walking 10,000 steps consumes roughly 134 kilocalories just from this gravitational work. Biomechanists model walking as an inverted pendulum, where speed and height exchange energy back and forth, about 65% efficient at the optimal walking speed. Running switches to a spring mass model, where the Achilles tendon stores and returns elastic energy. But running also dramatically increases air resistance. Drag force grows with the square of velocity. So running twice as fast requires 4 times the force against drag and 8 times the power. When you walk, your center of gravity doesn't travel in a straight line. It gently rises and falls. Watch the red marker at the pelvis as this figure takes a step. It reaches its highest point at mid-stance, when the body is balanced over a single supporting leg. And it drops to its lowest point at heel strike when both feet briefly share the load. The result is a smooth wave, about 5 centimeters tall, completing 2 full cycles for every stride you take. Usain Bolt's 9.58-second world record in Berlin in 2009 is a masterclass in energy management. His body mass was approximately 95 kilograms. At peak speed of 10.4 meters per second, his kinetic energy was about 5,100 joules. Yet his total energy expenditure over 100 meters was closer to 22,000 joules. Where did the rest go? Approximately 68% was spent overcoming air resistance. Drag force increases with the square of velocity. At sprint speeds, pushing the air aside requires far more energy than accelerating the body against gravity. This is why altitude records are consistently faster. Thinner air means less drag. And this is why Bolt's crouching start and upright mid-race posture were carefully optimized to minimize his frontal area. His peak power output reached 2,600 watts, approximately 3.5 horsepower. A human being for a fraction of a second. A T20 cricket match is a full body energy event. A fast bowler delivers about 24 balls in a match. Each delivery involves a 20-meter sprint, a complex biomechanical action exerting peak forces of 2,500 newtons and a release speed of 140 kilometers per hour. Over a match, a fast bowler can burn close to 1,000 kilocalories. A batsman hitting a 6 converts roughly 180 joules of muscular energy into ball kinetic energy in half a second, a power output of 360 watts. And do not underestimate chess. Magnus Carlsen's heart rate during critical positions has been recorded above 180 beats per minute, the same as a sprinter mid-race. The mental stress of deep calculation drives metabolic rate to 3 times its resting value. Your brain, like your muscles, runs on ATP. Energy conservation is not just an environmental slogan, it is an engineering imperative. Every kilowatt hour of electricity saved in India prevents approximately 0.9 kilograms of carbon dioxide from entering the atmosphere. Tamil Nadu's peak power demand exceeds 17,000 megawatts. If every household reduced consumption by just 10%, we could free up 1,700 megawatts, equivalent to shutting down 3 large coal power plants. Replacing a single 100-watt incandescent bulb with a 10-watt LED saves 90% of lighting energy. Tamil Nadu already leads the nation in solar and wind energy. Understanding power and energy quantitatively is the first step to conserving them intelligently. As engineers, this responsibility falls directly on you. Scientific notation becomes essential when we look at power on a cosmic scale. A resting human body dissipates 80 watts, 8 times 10 to the power 1. Tamil Nadu's entire grid peaks at 17 gigawatts, 1.7 times 10 to the power 10. That is a factor of 200 million larger than a human body. A lightning strike briefly reaches 1 terawatt, 10 to the power 12, but only for about 1 millisecond. The Krakatoa eruption of 1883 released energy equivalent to 200 terawatts sustained over several days. Earth itself radiates 44 terawatts of geothermal heat continuously. The sun radiates 3.8 times 10 to the power 26 watts in all directions simultaneously. Of this, Earth intercepts 1.74 times 10 to the power 17 watts, what we call the solar constant. Every hour, the sun delivers more energy to Earth than all of humanity uses in a year. The entire energy history of human civilization is less than 1 second of the sun's output. This is why solar energy is essentially inexhaustible, and why the prefix system from pico to exa is not academic luxury but daily necessity. Now let us scale all the way up to the most powerful machines ever built by humans. Rockets. Saturn V, which carried Apollo 11 to the moon in 1969, produced 34.5 million newtons of thrust. At launch, its 5 F1 engines developed approximately 100 gigawatts of power, more than the entire installed electricity generating capacity of India today. It burned through 10 tons of propellant every second. The total energy released in its ascent was about 250 gigajoules. SpaceX's Falcon 9 produces 7.6 million newtons and is reusable. The booster lands itself back on a drone ship. Starship, with its 33 Raptor engines, generates 74 million newtons, the most powerful rocket ever flown. Closer to home, ISRO's Chandrayaan-3, launched in 2023, used the LVM-3 rocket and successfully landed on the moon's south pole, a world first, at a total mission cost of just 615 crore rupees. For context, Avatar 2 cost nearly 5 times more. The kinetic energy needed to place 1 kilogram in low Earth orbit is about 32 megajoules. At TANGEDCO tariffs, that energy costs roughly 290 rupees. The rocket itself costs millions, because getting the fuel there efficiently is the unsolved engineering challenge of our age. Let us consolidate. 1. Power is the rate of energy. P equals dW by dt, mirroring velocity in mechanics. 2. Electrical units form a logical chain from the ampere outward. Engineering notation uses prefixes at every factor of 1000. 3. Your body runs at about 100 watts. Your brain uses 20. Chess and cricket demand similar energy. 4. At sprint speeds, drag force dominates over gravity. Bolt spent 68% of his energy pushing air. 5. Energy scales from picowatts in sensors to 3.8 times 10 to the power 26 watts in the sun. 6. Every kilowatt hour saved is real. 0.9 kilograms of carbon dioxide avoided. Tamil Nadu's renewable future depends on engineers who understand these numbers deeply. Before we close, remember these 3 relationships. Energy equals power multiplied by time. 1 kilowatt hour equals 3.6 megajoules. And power equals the derivative of energy with respect to time. The universe operates by the law of energy conservation. Energy changes form, it never disappears. As engineers, your job is to convert it efficiently, use it wisely, and waste as little of it as possible.